Hello and welcome back to the next episode in our quickfire tutorial series. In this episode I'm going to be revisiting terraforming and basically remaking my original video, as I had some concerns from people who found it not to be as clear as it could have been. As such, I'm going to be making a more comprehensive video that will go over each individual subject in a better light that should be easier to explain. Now, most people know what the idea of terraforming is, but terraforming in Aurora has various steps to it that I'm going to go through in order. The first is going to be colony cost and understanding the algorithms behind it and how it works. So, what is colony cost? Well, as you might know, if you opened up your system view or looked in your summary tab, you will notice this, which is colony cost, and you'll see various numbers. These numbers are determined by your colonies' costs, individual costs and algorithms. So I'm going to put on screen right now specifically the colony cost changelog for C#, and then I'm going to go through each of them individually. So, colony cost. Overall colony cost is the overall colony cost and the sum of everything here when combined into the maximum. So you can't, for example, have, this won't mean 50, but the highest colony cost here will equal the overall colony cost. So keep that in mind. Then you have acceptable gravity. Some worlds are low gravity worlds, and this is like Phobos and Deimos and Ceres, and they require low gravity infrastructure because of this. Another thing is going to be temperature factor. So, temperature factor. If the temperature is outside of the species tolerance, the colony cost factor for temperature is equal to the number of degrees above or below the species tolerance divided by half the total species range. For example, if the species range is from 0C to 30C, and the temperature is 75C, the colony cost would be 45 divided by 15 equal 3.0. The colony cost factor for tide-locked planets is 20% of normal. So in the given example, the colony cost factor would be reduced to 0.6. And there you go. So that is what temperature is, reading an excerpt there from the forums for Steve's changelog. So you obviously want humans to be in around 10 degrees, 5 degrees to like 40 is probably safe for you. And if you want to know your exact tolerances, you can go up to here and you can see your species tolerances. So ideal temperature is 14 degrees. Maximum temperature deviation is 24, so we can go 24 up or down. So we can have 38 degrees Celsius. We can have into the minuses, a little bit into the minuses. Okay. The next is going to be breathable atmosphere. So to be classified breathable atmosphere, it needs to have breathable gas, and the atmospheric pressure needs to be correct. So we'll go over breathable gas in just a second. Here we go. If the atmosphere does not have a sufficient amount of breathable gas, the colony cost factor for breathable gas is 2.0. If the gas is available in sufficient quantities but exceeds 30% of atmospheric pressure, the colony cost factor is also 2.0. So, for humans, you need oxygen, obviously. But you can't just have a pure oxygen world. You're going to need 30%, below 30% oxygen to be able to do it. And for humans, you need 0.1 atmosphere to be able to be breathable, which is this number here. So percentages makes up the total atmosphere. So the atmospheric pressure is 1.01, and then we have nitrogen takes up 0.79 of the atmosphere, oxygen takes up 0.2 of the atmosphere, and that goes into what the percentages will be. and that generates into the atmospheric pressure. Venus, for example, has a pressure 100 times that of Earth. So keep that in mind. And going into atmospheric pressure, if atmospheric pressure is above species tolerance, the colony cost factor for pressure is equal to pressure divided by species max pressure with a minimum of 2.0, for example. If a species has a pressure tolerance of 4 atmosphere and the pressure is 10 atmosphere, the colony cost factor would be 2.5. If the pressure was 6 atmosphere, the colony cost factor would be 2.0, as that is the minimum. So, this is to represent the fact that if you have an extremely high pressure world, the atmosphere is very pressurized and there's tons of atmosphere, it's going to be a pretty hard time to live on. And you can check what your race is pressure tolerance is here. So anytime you want to know what I'm talking about for your race, for humans, this is what you're looking at. So ideal oxygen pressure is 0.2. Ideal atmospheric pressure, maximum atmospheric pressure is 4.0. So anything above that, and humans are not going to have a great time, and that's going to cause colony costs to rise. Okay, next we have dangerous atmosphere. Now this is to represent dangerous gases such as carbon dioxide, chlorine, sulfur dioxide, all of these things that are harmful to human life. So you may know in real life, gassing people with chlorine, it's not the best for people. People can't breathe in chlorine. So here's how the mechanics work, and I'm going to put that on the screen really quick. If a dangerous gas is present in the atmosphere and the concentration is above the danger level, the colony cost factor for dangerous gases will either be 2.0 or 3.0. Depending on the gas, different gases require different concentrations before becoming dangerous. Halogens, such as chlorine, bromine, or fluorine, are the most dangerous at 1 part per million, or 0.001%, something like that. Don't quote me on that. Followed by nitrogen dioxide and sulfur dioxide at 5 parts per million. Hydrogen sulfide is 20 parts per million. Carbon monoxide and ammonia are 50 parts per million. Hydrogen, methane, if oxygen breather, and oxygen, if methane breather, are at 500 parts per million. And carbon dioxide is at 5,000 parts per million, or 0.5% of the atmosphere. Note that carbon dioxide was not classed as a dangerous gas in the previous version of Aurora, which was VB6. These gases are not lethal at those concentrations, but are dangerous enough that infrastructure would be required to avoid sustained exposure. So it's not telling you that carbon dioxide is going to kill you. Well, it will kill you in high concentrations, but it is going to, at certain points, get very irritable, and going outside without infrastructure or living without infrastructure is going to mean it's going to be quite an annoying experience. So these will go up according to their colony cost. So if this was 2.0, that'll be 2.0. If we look at Mars, we can have a look. Breathable atmosphere, dangerous atmosphere, and 2.12 there. And that's how that works. And then we see atmospheric pressure. If it can retain the atmosphere, it'll say here. And then water available. So in C#, there is a new mechanic to terraforming. That being hydroextend. This is to represent the liquid hydrosphere or the ice hydrosphere, it's both liquid, that is on a planet and is required for life to be sustained there. So you're going to have a much harder time living on a cold desert with no water than you are going to have a time living on a fresh jungle world, or fresh plains, or fresh temperate forest. So, as you can see, Earth has a 70%, 69.7% liquid hydrosphere, and that means 69.7% of the planet is taken up by liquid. Now hydrosphere, I'm going to read off here. Hydrosphere, if less than 20% of a body is covered with water, less than 20% hydroextent, the colony cost factor for hydroextent is 20 divided by 10, which is a range from 0 to 2.0. So, basically, how hydroextent works is that if you don't have enough water below 20% minimum, you are going to have issues with water available, and that's going to increase your colony cost. But hydroextent also plays into max population. So, for example, if I have a world, I'm going to bring up a world here. This is, where is it? Bernard Star. 98.9% liquid, so there's only 1.1% of the planet which has land on it. So that means that I can only support a population of 590 million people with a diameter of 28,000 kilometers in size. So even though this planet is more than double the size of Earth, I can only support a population of 519 million people on the planet. And this means that you need to reduce the hydro extent. And I'm going to get into this next part where we go over terraforming mechanics themselves. But this is just to get you a base idea of how the colony costs work and what you're looking at when you're looking at a planet. So keep that in mind. So, let us go. Also, there's crustal, which is basically just hydro extent, and it kind of models other things. Keep that in mind. Okay, so now we're going to go over to our terraforming tab. So you'll find your environment tab here, and you'll want terraformers in orbit. A terraformer is a ship or station with a terraforming module on it. You can also build terraforming installations and ship them to the place you want to terraform, and those require workers to be used. So keep that in mind. So as we can see, we have our very familiar colony cost window here. So we have overall colony cost, temperature factor, breathable atmosphere, dangerous atmosphere, atmospheric pressure, water available, accessible gravity, and atmosphere retention. Now, what do all these numbers correlate to each other? Well, we've already talked about how colony cost affects things, but we are now going to talk about some of the more basic mechanics. So I'm going to put on screen Terraforming Update, which is going to show you some of the general mechanics around it. So, first off, the base terraforming technologies have been reduced by 75%, and you'll see this over here. So if we look at Mars, annual terraform capacity is 0.103, and that is because I have 2 terraforming stations in orbit with 5 modules each, and they provide that much atmosphere change or terraforming change a year. The rate of tech increase has improved, so the higher tech levels are reduced by around 60%. The starting racial tech rate per module / installation is 0.00025 atmosphere per year. So that'll tell you what you need. Then you have terraform rate versus Earth. So because Mars is a smaller planet to Earth, about 5,000 kilometers in diameter smaller, it's 3.52 times faster terraforming in comparison to Earth, or 2.52, I guess it would be. Lunar is 13.48. So big worlds like Caprica or Bernard Star, Solaris here, is 0.2, so it's 80% slower than terraforming on Earth. While on Mars, it's much quicker. So this means the bigger the body is, the harder it's going to be to terraform that body, but the more reward you're going to get from terraforming that body to be habitable, because it can support a bigger population. Then we have radiation and atmospheric dust levels. Now this happens when you nuke the planet, and I go into that in my Xenocide episode for my 100 subscriber special, so I'm not going to go too much into that. Then we have the hydrographic extent, which is the current hydrosphere, essentially. And it'll show you how much you have in it. Then you have surface temperature in Kelvin, base temperature in Kelvin. Those aren't that important. Then you have base temperature in Celsius, and then surface temperature. Surface temperature is what you want to be looking at for when you're determining your temperature factor. So Mars is very cold at minus 60 degrees Celsius, and so we have a temperature factor cost of 2.124. Okay, then we have our atmospheric pressure. So we have different levels of pressure that are exerting on the atmosphere. There's only 0.006 atmospheres in Mars' atmosphere. And as you can see here, we have some argon, we have some nitrogen, we have water vapor, because I'm currently pumping water vapor in to create more hydro extent, and carbon dioxide. So all of these numbers will then go into these numbers. Up here, you can select which gas you want to add to the atmosphere. Now, I'm going to talk a little bit now about water vapor and also system gravity. So, system bodies with gravity of less than 0.1 g cannot retain an atmosphere and cannot be terraformed. So very small asteroids cannot be terraformed. Keep that in mind. Water is a significant factor in terraforming planets. Water vapor can be added to the atmosphere just like any other gas. So I can add water vapor to the atmosphere. You add it by clicking this checkbox and typing in how much vapor or how much atmospheres of that gas you want to add. F here means frozen, just so you know. And water vapor is not what you want. You want the stuff that it condenses into, as it will condense out of the atmosphere into the hydrosphere. And how it works is water vapor will condense out of the atmosphere at a rate of 0.1 atom per year and increase the planet's hydro extent. So you can add water pretty fast to a planet. Give it, if you have enough terraformers, you can do it extremely fast. Each 1% of hydro extent requires 0.025 atoms of water vapor. So that means that you're going to get every year, if you have 0.1 atom of water vapor in the atmosphere, every year you'll create 4% of hydro, 4% of hydro extent. And so keep that in mind, and that would mean that you would require 0.5 atom of water vapor to get 20% hydro extent. And while that seems like a long time, on smaller worlds it will go much, much faster. Water will also evaporate into the atmosphere. The evaporation cycle follows condensation and will stabilize water vapor in the atmosphere of a planet with liquid water of a level of atmospheric pressure times hydro extent divided by 100 times 0.01 atmosphere. The resulting atmosphere times 20 is the percent of the planet's surface that loses water, as the water vapor is removed from the atmosphere. It will replenish from the surface water. This is to allow the removal of water from ocean worlds to create more living space. So, if you, for example, have this world over here where we have 98.88% hydro extent, you're going to want to remove that. And you can remove any gas and water vapor by just putting in the amount you want to remove and unchecking this box. So keep that in mind. Then, for the rest of the gases, you can add them appropriately with here. So, for Mars, I'm going to want 0.1 atmospheres of oxygen, and I want less than 30% because of the rules we discussed before in our colony cup. And then I want to get rid of the carbon dioxide because that's toxic. So it's a game of really just trying to get these numbers to zero to give you zero colony costs so you don't need infrastructure. For every colony cost, you're going to need 100 times that in infrastructure, right? So I have 2.12 colony cost here, and that's meaning I need 212 infrastructure per million population. So, and it will also then affect your population because, as you can see here, I'm having to put a much larger percent of my population, 3 times as much, into agriculture and environmental sectors rather than Earth, which has only 5% of its population, into those sectors. And this still represents terraforming jobs and people trying to keep others alive. And this is why people recommend building stations with terraforming modules. Alright, now that I've explained the base mechanics and I've gone over each individual thing, let me know how you thought about the video. If you enjoyed it. This went a little longer than I wanted for a quickfire tutorial series, so I will be adding this to a terraforming playlist, so it's easier for you guys. Let me know if I miss anything or if I need to cover anything in the next episode of this series that I'll now be doing for terraforming. And let me know if you did understand it all well and good. I'll see you next time. Remember to like, follow, and subscribe. Bye-bye.